from the object recognition side, we want to learn the object models from point cloud data, probably, maybe also different sensors that the PR2 provides. Here you can see preliminary work from Bastian Steder, who's now an intern at Willow Garage. You can see how the robot takes a point cloud of a room, and obviously the point cloud doesn't give you enough data to actually be useful, so you really need to segment it and detect the objects in there. And you can see this in the visualization of this video. Now that we have this object information, we can store it in a map, and it can become available to symbolic planners that can then work on a completely different level to actually generate plans to move a chair away or bring the book back to the cupboard. The general approach here is that we are going to match feature points from the models with the point clouds from the sensor data of the robot. From that, we can then estimate object candidate poses, and finally score and filter these candidates. From the articulated objects side, we want to be able to detect articulated objects. Articulated objects include doors, but they also include drawers or office cabinets and cupboards and so on. And we not only want to learn these models, but obviously we also need the PR2 to actually interact with them, use them. And one important aspect here is also that the PR2 is able to recognize that it can store objects in a cupboard or get it out from a cupboard and remember which objects belong in which of these storage objects in a domestic environment. The generalized mapping, as I said before, is like you can imagine it as a topological map. We also want to deal with multi-floor buildings, multi-story buildings that we augment with semantic information, and that includes information about the detected objects, also the articulated objects in the world or in the home, all the kinematic models that we learned for them, and also the action and skill models that we have learned by interacting with these objects. And this allows us to provide a symbolic description of the world to the planner. And the planner then needs to generate a high-level plan that brings the robot to all of the places and makes it do all the things that we want it to do. The problem that you can imagine is that the robot obviously only has incomplete knowledge. And that's especially hard when you want to make a plan, because you can make the plan only until a certain so you cannot generate a full plan, but you have to. So for example, the robot comes to the living, or you tell the robot, please clean up the living room table, and the robot is now in the kitchen, so it can only think as far as that it has to go to the living room, and there look around for the objects. Maybe the table is already clean, or maybe there are 3 or 5 objects, and then it needs to extend the plan after it has seen that. So we want explicitly to include sensory actions that produce knowledge in the symbolic planner. We also attach assertions to them, like pre- and post conditions, and these post conditions can then also trigger replanning. So the robot can think, well, I will look in the living room, how the table looks like, and then I will make the next part of the plan. And then there is a second thing to it. Not all real-world facts can be well represented on a logical level. So you want to have some skills of the robot that are on a sub-symbolic level to be efficiently executed by other modules, like, for example, the path planning part and so on. So yeah. And then lastly, we have the action skill learning. That's what the machine learning group will implement. It's about that the robot, so maybe we have a hard-coded solution for opening doors, or we have a hard-coded solution for grasping an object, but in the end you would like to optimize that, to make the robot learn from experience and be able to improve its actions that it already has. And we also like to extend that to that the robot is able to acquire and provide new actions, and that it can identify constraints that can then be integrated again in the semantic attachments of the semantic map. And we want to evaluate our project continuously in the next 2 years. So finally, we want to have that the robot is able to execute this task, this cleaning up task, reliably. That means that in more than 90% of the trials. We also want to show that, and that's a nice thing about the PR2, because now all of you guys have also PR2s, so we can come to visit you and test our application at your lab to show that it's also working in different places. And we also want not only to publish our code open source, but we really want you to use it and make it useful for you. And therefore, we will come and visit other labs and see how our code could be useful for you and make it available to you. So we will contribute 5 open source modules as part of our Freiburg ROS package repository. We have the graph-based map representation, the 3D object detection and localization, the model learning for articulated objects, the symbolic planner that will interact with the graph-based map representation, or all of these modules will interact with each other, and the manipulation skill learner. So to conclude, our project is a joint initiative of the AI and robotics groups at the University of Freiburg. The project is called TidyUpRobot. It's about the reliable execution of fetch and carry tasks, like cleaning up the table in the living room. And we are looking for labs that would be interested in that kind of application or in these individual modules, such that we could test our application in your lab or make you familiar with our code and our modules. Okay, thank you.